All right, in this next video, we're going to look at voltage drop across a parallel or combination circuit. So we have this example circuit here. We have an 18-volt power source, and we have resistor 1, which is 5 ohms, and then we have a pair of resistors in parallel here. R2 is 8 ohms, and R3 is also 8 ohms. All right, so before we get started, let's look at the fundamental equations that are going to help us to solve this problem. So we already looked at the Kirchhoff's law, voltage equals the current times the resistance, V equals IR. But in a parallel circuit, these equations take on a different form when we're talking about multiple components here. So in a parallel circuit, the total voltage is equal to the voltage at any point. Okay, so V1 is equal to V2 is equal to Vn, right? They're all the same. The total current is equal to the sum of the individual currents. All right, so that means that I1 plus I2 plus ... IN is equal to the total current when we add all those up. All right, and kind of the one that the trickiest one, or the one that takes the most to remember, is the resistance. Okay, so the resistance in a parallel circuit right here, 1 over the resistance total is equal to the sum of 1 over the individual resistors. Okay, so that means 1 over R1 plus 1 over R2 plus ... 1 over R3, okay, is equal to 1 over the total resistance. All right, not resistance total, but 1 over the total resistance. Okay, so now these equations are going to help us for part of this problem. It's important to understand that this is a combination circuit. So this is the parallel part right here. This is where the parallel resistors are, and this is where we're going to be using these equations to help us to simplify this. But we also have another resistor, resistor 1, which is going to end up being in series with this. Okay, so the way that we're going to solve this is, first we're going to simplify this. Okay, because we can't really deal with it like this. All right, so how do we simplify it? We're going to get an equivalent resistance, okay? And then we're going to basically have an equivalent resistance that we can then put in series with resistor 1, all right? So what is this equivalent resistance? Well, let's call it R23, all right? And R23, let's say 1 over R23, is equal to 1 over R2 plus 1 over R3, right? So we just took that equation right there. So 1 over R23 is going to be 1 over R2 is 8 plus 1 over R3, which is 8 ohms. Okay, so 1 over 8 plus 1 over 8 is 2 over 8 ohms, okay, which is equal to 1/4 or 0.25 over ohms. Okay, don't forget the where the value goes, where the unit goes. All right, and 1 over R23 is equal to 1 over 4 is equal to 0.25 over ohms. Right? Just to write this out so you can see it in different forms. And so therefore, resistor 3 is equal to 4 ohms. Okay? So the equivalent resistance for this pair of parallel resistance is 4 ohms. So we can essentially rewrite this circuit like this: 18 volts where this is now R1 and this is now R2, 3, all right, which we know is equal to 4 ohms, and we know R1 is equal to 5 ohms. Well, this should look very similar to the last problem that we did, where we have a pair of resistors in series, right? And we can deal with that very easily. We know what the total voltage is. The total voltage is 18 volts, right? So we can say V equals IR. 18 volts is equal to I, we don't know what the total current is, times the total resistance, which is in this case is going to be 5 plus 4. 5 ohms plus 4 ohms. Remember that in series now, the resistors add. Okay? So this is going to be 9 ohms, right? And so therefore, the total current is going to be 18 divided by 9, or 2 amps, right? So the total current across or in this circuit is going to be 2 amps. All right, so where do we go from there in terms of the the solution for, remember that we're still working on the voltage drop. Well, we can actually do the voltage drop across resistor 1, right, because we have everything that we need. So we can say that V equals IR, right? But now we want to do the voltage drop across 1 is equal to, let me move this up a little bit. The voltage drop across 1 is going to be I1 times R1, okay? And we know that I1 is the same as I total, right? Because we're talking about a series circuit now. We've deconstructed this circuit back to a series circuit because series circuits are very much easier to deal with, okay? So this is going to be 2 amps times the resistor 1, which is 5 ohms, right? So that's equal to 10 volts, right? So the voltage drop across resistor 1 is going to be 10 volts. So the amount of work that we need to do to force the current through this first resistor is 10 volts. Okay? Now, we can also do the voltage drop across the equivalent resistor, R23. Now, this isn't a real resistor. This is the equivalent of this parallel circuit, but still, in order to solve the voltage drop across R2 and R3 individually, we need to do the equivalent voltage drop. So we can go V23 is equal to I23 times R23, okay? So we know that I23 is the same as I1 is the same as I total, which is 2 amps. So 2 amps. Remember, that's constant for a series circuit, and this is a series circuit now. And R23 is 4 ohms. So this is equal to 8 volts. Okay? So the voltage drop across this equivalent resistor is 8 volts. 8 volts. All right? Now, we need to figure out how we're going to get the voltage drop across these individual resistors. Okay, so let's continue where we left off. So we have the voltage drop across the equivalent resistor 2,3 that represents this pair of resistors in parallel. So what I'm going to do is I'm just going to redraw this a little bit so we have something that we can see. Okay, and we know that R1 or R2 is here and R3 is here, and R2 equals R3 equals 8 ohms. Okay, so that's what we had for the, let me dim the lights a little bit here. That's what we had. There we go. Maybe that's better. All right, so that's what we had for the circuit. Now we know that the voltage drop across 2, 3 is equal to 8 volts, right? So in a parallel circuit, right? Remember, in a parallel circuit, the voltages are all equal, right? The voltage stays constant. So the V total voltage is equal to the individual voltages. So that means that if the total voltage is 8 volts, that means we have 8 volts running across here and 8 volts running across here. Okay? And so that's going to be the voltage drop across these two resistors. Now we can calculate how the current changes, right? So we know that V equals IR, right? And so, excuse me, let's do this. Let's do voltage, excuse me, yeah, voltage 2 is equal to I2 R2, okay? What is voltage 2? Well, again, it's the same as voltage 2, 3. It's 8 volts, right? So we have 8 volts coming across here. So we have 8 volts is equal to, we don't know the current, but we do know the resistor. The resistor is 8 ohms. 8 ohms. So the current across 2 equals 8 volts divided by 8 ohms equals 1 amp. Right? And obviously that's going to be the same here, right? Because we have the same resistor value. So I3 is equal to 8 volts divided by 8 ohms, 2 or 1 amp. All right. So there's your calculation for voltage drop for both a parallel and a series circuit. And different ways that you can calculate it. Remember that the voltage drop, maybe the term is not the best term. I certainly would concede that point. And it might be easier to think of voltage drop as the amount of work that's required to push a current through a resistor in this case. And so in each one of these examples, we need 8 volts of 8 volts to push the current through this resistor, 8 volts to push it through this resistor. And if we look at the resistor resistor 1, we need a total of, where did we put that? This is resistor 1. Where did I calculate it? Resistor 1. We need 10 volts to push the current through resistor 1. Okay, so hopefully that answers any questions. Oh, there was also a question about switches and voltage drop across switches. You really shouldn't have a voltage drop across a switch. You might have a very slight minimal voltage drop across a switch just because of the internal resistance of that switch. You know, everything in real life, everything is going to have a little bit of resistance, even wires. And so there would be a slight voltage drop across a switch based on just the wiring or the internal resistance of that switch. But essentially, for a theoretical switch, there should be no voltage drop across it. Okay, I hope that answers any of your questions. Please let me know if there are any questions that you have.